Good afternoon, everyone. Thank you for joining us. My name is Claire, and I'm a contract librarian on assignment here with NOAA Central Library. This seminar series is offered through the NOAA Central Library Seminar Program, which provides an educational forum for the presentation of ideas, research updates, and news in support of NOAA's mission. Before I start, I have a few technical tips for attendees. Just so you're aware, you are muted and you're not able to unmute, but if you have a question, you can type it into the question panel and we'll get to those during the Q&A session at the end of the presentation. If you're having any audio or visual issues, for example, if you can't hear the speaker or see the slides, please try logging off GoToWebinar and logging back on, and that will solve most issues. And just as a reminder, this is being recorded, so if you'd like to revisit the seminar or view previous seminars, you can find them on our YouTube channel. So now I'm going to turn it over to Peg, who's going to introduce our speaker today.
Thank you, Claire. Yes, this is Peg Brady from NOAA Fisheries. And, excuse me, welcome again to our continuing EBM/EBFM seminar series for 2022. Today we're continuing the series that initiated back in November 2017. And our purpose has been largely to increase awareness regarding ecosystem-based management, or fisheries management in particular. And today we're taking a slightly more focused discussion on economics and human dimensions as it relates to marine ecosystems and the benefits that we derive from those marine ecosystems. We want to continue to thank NOAA Library, who's been our co-host since the beginning. And the seminars are typically held the second Wednesday of each month at 3 p.m. Eastern Time. And as Claire indicated, these presentations are accessible via the YouTube channel. So visit the YouTube channel to see our past presentations. I want to thank many of our past speakers and those who attend and those who offer recommendations about future topics to cover in this series. So I'm very happy today to introduce John Walden from our Northeast Fisheries Science Center, who has co-authored this presentation with Garrett Piper, both members of the NOAA Fisheries Economics and Human Dimensions team. And I also want to acknowledge Doug Lipton, our senior research economist, who has suggested that we focus in on these issues in these presentations, the seminar series. And we're hoping to add more in the future. So stay tuned. And again, thanks, John, and thanks to you and Garrett for putting this presentation together. We look forward to listening to it and having some question and answer later on. Thank you so much, John.
All right, thank you, Claire, and thank you, Peg, for that introduction. Before I begin, I need to acknowledge Garrett D. Piper, my co-author on this, who is really helping me understand ecosystem issues and how to frame this research. I also need to thank members of the Human Dimensions Working Group, which is part of the Integrated Ecosystem Assessment Program within NOAA, for their comments and suggestions on this research. For those of you who don't know me, most of my work over the past several years has been centered on performance measures for our commercial fishing fleet. And this is really our first attempt to cross over and use some of those same methods to look at what we're calling ecosystem performance. So in terms of what I'm going to cover today, the first half of our talk will really focus on why we undertook this project, and we'll develop the methodology that we used. I'm going to spend a bit of time explaining why we chose the index numbers we did and details about constructing those indices. Index number construction is a narrow but really important field within the economics profession, and I want to do my best to try to explain our thoughts behind the indices that we created. The second half will be an application of the methods to a specific ecoregion. So we all know that marine ecosystems provide a wide variety of goods and services, and they're really supported by a complex and dynamic marine environment. If you look at the stats, the ecosystems report that our ecosystem group produces in the Northeast region, there are dozens of different indicators being used to describe the environment. And so the question really becomes, from my mind, given that you have all these outputs and environmental conditions and perhaps different measures to report on them, how do managers evaluate whether their efforts are leading to improved outcomes or not? Can we make sense of them all? So can we take these various indicators that are being developed and collapse them into one or two composite indicators that really give managers and people that are interested in ecosystem performance an idea of how the ecosystem is doing. The problem is, you know, in order to collapse all these indicators, there needs to be a method to weigh the outcomes and environmental conditions in such a way that we can get a composite measure. And so ultimately what we're trying to do is address this weighting issue and construct index numbers which can inform managers about their performance in terms of how the ecosystem is doing in terms of goods and services and the underlying conditions, and see how it's changed over time. As I said at the beginning, this is really the first time we've attempted to do this in the ecosystem context. What I mean is create these performance measures. So what I'm presenting to you is really a proof of concept paper. So if you look at some of the documents about ecosystems and marine ecosystems, you know, we categorize ecosystem services and what's being produced in a variety of ways. So for marine ecosystems, here are some of the categories that we've thought are important. And so seafood production is important. And we look at landings and how landings have changed over time. We're also interested in profits for the commercial fishing fleet. And we generally use revenue as a proxy for profits in many cases because we don't have really enough cost data yet to do a profitability measure. Recreational activities within an ecosystem are really important, and so we measure days fished, recreational trips, recreational catch. People are also interested in social and community, social and cultural aspects. You know, for the communities that border the ecosystem, and for those that use the ecosystem and depend on that. So we look at community engagement, how engaged people are in that ecosystem, and reliance, you know, how they rely on the ecosystem. There's also a protected species dimension to this. In the Northeast, as you all know, we have the most endangered marine mammal there is, the northern right whale, and we also have other protected resource issues such as harbor porpoise being entangled in commercial fishing gear, and also there's issues with leatherback turtles being entangled in fishing gear. And underlying all these kind of outputs, there are supporting services coming from the ecosystem itself. You know, things like the underlying biomass, the productivity of that biomass, the trophic structure, and the habitat. So for this particular project, we really wanted to assess the ecosystem performance across multiple outputs and inputs. I was already working on creating indices to measure performance of commercial fishing fleets, and I thought that index numbers would be a natural fit for this project. So we want to properly construct index numbers to look at the social and environmental change that's taking place. And we want to use those indices that we create to determine whether the environmental, what I'm calling environmental performance, has improved over time. In the end, we're trying to get a combined index which shows outputs per unit of environmental input and communicate how this is changing throughout time. I'm not sure how many people are familiar with index numbers. If you've been paying attention to the news lately, you probably heard a lot mentioned about inflation and the consumer price index. And so most people are probably familiar with the CPI. And I think yesterday there was a news clip that came out and said it's rising at an 8.5% annual rate. So the price index is something that's used to look at how prices for a basket of goods and services change over time. And there's the Bureau of Economic Analysis creates lots of them. There's a consumer price index, producer price index, there's seafood price indices, there's a lot out there. But what we're really wanting to get at is the flip side of these. We want to get at quantity indices. And really, for those of you who are familiar with fisheries, CPUE is really a quantity index when it comes right down to it. What you're measuring is you're trying to aggregate some measure of catch and take the ratio of that catch to a measure of effort. And in a multi-species setting, you have to aggregate that catch in some way. And effort is also a multi-dimensional product that has to be aggregated to come to a single number. So really, to do these, what I'm calling basket type quantity indices, where several outputs or inputs are grouped together, you need to come up with a good weighting scheme. And so that's really the crux of the problem: how to get to this weighting scheme and what to use. Over the past several years, I've been working with economists at the University of Queensland, Chris O'Donnell, and he really impressed on me this notion about the index numbers being consistent with what he calls measurement theory. And measurement theory simply says that an index number can't be assigned in an arbitrary way, that they must be assigned in a way that the relationship between the index numbers mirrors the relationship between the baskets that are being measured. And I'm going to give you a real simple example of that. So here's a simple example, and I have 4 baskets, A, B, C, and D, and I put my favorite, well, 2 of my favorite foods in here. I have peanut butter and honey. Okay, and what I've created is what we call an additive equal weight index. So I'm weighting both of these items by 0.5. So you notice that basket A, when I do that, the index number I get is 1. And then basket B, I have 2 peanut butter and 2 honey, and I get a value of 2. And then C, I have 3 and 3, and I get a value of 3. And then finally in D, I have 4 of each, and I get a value of 4. And so this is what I mean by the index numbers have to reflect the relationship between the baskets. We know that B is twice A, and we know D is 4 times A. So if B was coming out as 2.2 and C was coming out as 3.3 and D was 3.9, we know there was a problem with our index number. It wouldn't reflect the reality of the differences between these baskets. So you could actually do this type of index for our ecosystem. But the problem is, well, you could use this equal weighting aspect. You could do an additive equal weight index. But the problem is, you're basically saying that everything in your basket should be equally weighted, and you're putting equal weight on that. And we don't really know if that's how society in general weights what's coming out of the ecosystem. You know, what's more important. You know, so you could get it. You know, you'd be weighting, let's say, endangered species the same as you did recreational fishing opportunities. Really, what we're trying to get at is this weighting scheme, and using a different type of weighting scheme to try to come up with an index number that makes sense, is consistent with measurement theory, and explains the differences that are going on within the ecosystem. So how do we do this? You know, in economics, usually prices are used to weight quantity indices, and that works really well, except that in an ecosystem context, we don't have prices for many of the goods and services. For seafood, for fisheries landings, for the landings that are coming out of the ecosystem, we can price those really easily. I mean, that's an easy thing to do because we have market prices, and we can find a way to get a good price to apply to our index. But if you think of something like a right whale, how do you price that? Economics can value that. There's studies that we can do that, but those studies are very expensive. They're very time consuming. It would be hard to replicate them year after year. And then for the supporting services, think of chlorophyll A, something that's part of the environment. You know, how do you price that? You really can't. So what we do is we use something called Data Envelopment Analysis. And we use data envelopment analysis to estimate distance functions to create our indices. And by doing this, our weights that we're using to create these indices are based on the historical performance of the system. So the models are creating a weighting scheme that basically uses what's taken place in the past to weight our inputs and outputs in our system. I'm not sure if how many familiar with distance functions, but literally distance functions are a measure of distance. And in what we're trying to do, a distance function is revealing the distance, the greatest output expansion possible or the greatest input contraction possible for an observation to be placed on an efficient production frontier. And I'm going to give you an example of that in just a minute. Data envelopment analysis has been around for a while. This definition I have up here is a technical one, and it was created in 1978. It was basically looking at businesses and how they allocated their inputs and what they produced. So it talks about decision-making units and for businesses or for a public sector agency. But it's been used for a wide variety of studies. It's used to develop for the Human Development Index that's produced by the United Nations. It's been used for environmental studies looking at environmental performance. It's been looked at for firm and plant level performance. I used it in the early 2000s to measure capacity of our fisheries. It's used for productivity measurement fisheries. In fact, actually this morning I did a simple Google search for data envelopment analysis, and I got 4 million results. And then I went to Google Scholar and did the same thing and got 226,000 hits. And then I looked at that Charnes, Cooper, and Rhodes. I looked that up also on Google Scholar, and there's over 41,000 citations. So I'm just throwing it out there so you have an idea that this is a very widely used technique, particularly in the economics profession, and it's been used widely for a variety of studies. So I'm just going to give you a quick example of what DEA does. So here, the strength of data envelopment analysis is really the fact they can deal with multiple outputs and multiple inputs. It deals with multidimensional problems really well, but it's really easy to explain in 2 dimensions. So if you just look at this slide, we're talking about input-output combinations of I'm saying years. So we have an input, and you can think of this as an environmental good or environmental input, whatever you want to think of. And the output, you could also think of that as an environmental good. And then you have these observed points, right, that we have over time of how inputs map to output. All right, so you have this spread of points. So what data envelopment analysis does, and I'm showing an output-oriented model, it traces out this best practice frontier, what we're calling. And so these points on the best practice frontier, on the linear segments, are really the most output you get for a unit of input given your observation. So, for example, 5.9, you can't get any more output for 5 units of input. That's what that's saying. Anything to the interior of this frontier is considered inefficient, and you should be getting more output for your unit of input. So, for example, here, the 0.89, for 8 units of input, you're getting 9 units of output. Well, you have another observation for the same input, you're getting 12 units of output. So this point at 8.9 is inefficient compared to the 8.12, and the distance here between the 2 points is what the distance function measures. And I think the value of this would be 0.75. It's 3/4 as good. So you should be able to boost your output to 12 from this point. If you go over here to this point 12.12, it's being projected up to the frontier based on a convex combination of this point at 10.13 and this point at 15.15. So the model is weighting these 2 points and boosting this up to its highest level. So these output-oriented models are trying to expand output given a fixed level of input. Now there's also an input-oriented version of this. And so, for example, at the same point 12.12, you should be able to produce that with 8 units of input. So the input distance function is going to tell you that for 12 units of output, you should be able to contract your input from 12 to 8. So this is inefficient from both an input perspective and an output perspective. So here's how we define our indexes. And we take advantage of both our output distance function and our input distance function. And so y is a vector of outputs and z is a vector of environmental variables. So first I'm going to define what I call the output quantity index. And it's simply using this output distance function. So for time period k, the vector of outputs in time period k is evaluated. The distance function is calculated given this reference value of environmental inputs. Okay, and then that is compared to the distance function in time period L given the same reference set of environmental factors. You can also do the same thing with an environmental, I'm calling this an environmental input quantity index, but we're using the input quantity index or the input distance function. So in this case, we're setting a reference level of output and looking at the environmental factors in period K. So what that's saying is that what is the least environmental input you'll need in time period K to produce this reference vector of outputs. And then it's the denominator is the same thing, but you're using time period L and to produce this reference vector of outputs. And then what you can do is you can combine the two. So you take the output quantity index and divide it by the environmental input quantity index. And for lack of a better term, I'm really calling this an output environmental input quantity index. And so really, to me, it's telling you the output you're getting per unit of environmental input, or maybe you think of this as the output you're getting given a certain level of environmental quality, if you want to look at this as an environmental quality index. So how do you do these with data development analysis? So what we actually calculated is the inverse of those data functions, those distance functions. We're calculating their inverse. And so what we're doing, this is the output-oriented model. And so we're trying to expand this data term. This is a linear programming problem. And what you're actually doing is you're estimating it once for each year or observation in your data set. And we've programmed these in R and they went really quick. I can do all 4 indices in less than a second. So it's just really fast. So you're maximizing this data term, and then this is your constraint set. And there's one equation for each environmental output in this case. So you're putting this on the right-hand side, and what you're doing is this lambda term here, it's a weighting factor, and it's putting weights together for all the observations in your data set so that this equation will hold. And what's constraining this is this equation here. This is your environmental inputs. This is your reference vector. And there's one equation for each environmental input. And it's using, the weights are also being formulated based on this relationship. And then this final equation means, I put it in there because it ensures that the model actually solves at each iteration. You don't get infeasible solutions, which is always a problem with LP models. So that's the numerator for that quantity index. And then the denominator, it's the same program, but what we're doing is we're using a reference vector for both the outputs and the environmental inputs. So the equations are exactly the same, but the right-hand side is different for the output. And so in practical terms, what you get for this particular denominator is you're going to get one value. Every year is going to have the same value. So you're basically normalizing this numerator by this one value you're getting out of the denominator. The environmental input quantity index, the QZ, it's the same. It's the same, except we're using an input distance function. We're trying to minimize this theta term. So in this case, we have a reference vector of outputs here on the right-hand side, and then this is the environmental input for each year that you're doing the model for. So you're trying to shrink this. You find the minimum value of this that still allows you to get this level of output. And so this is I should have mentioned this before, this is a radial expansion or a radial contraction. So it's basically trying to contract all the values of the environmental inputs equally. The denominator is the same problem, but again, we're using a reference vector for both inputs and outputs, and you get one value coming out of this, but the program is exactly the same. It's just the right-hand side variable for Z is changing. So I put together a small example. I did this actually at the beginning of the project because I wanted to make sure that this program actually worked. You know, I wanted to make sure that the index numbers that we're getting out of here made sense. And so, you know, I presented you with a lot of math and equations, and maybe, you know, those DEA models look a little funny and you know, look a little strange. So I put this together to sort of show that it works. So what I have is 20 years of data, and I randomly generated this data, and I have 2 outputs and 2 inputs, and for a couple different observations, I change what I'm getting just so I have a reference so I can see that this works like it should. So here are the outputs, Q1 and Q2, and you see in year 2 we have 8 and 7, in year 4 we have 8 and 7. So if you look across at the index number we're getting out of this, we have 1.37 and 1.37. They're exactly the same, and that's what we should be getting because these bundles are exactly the same. If we go down to year 11 and year 16, we get 4 units in year 16 and 2 in year 11. And you can see that the index is 0.74 in year 16 and 0.37 in year 11. This is twice this, you know, and it reflects the difference. This bundle is twice this bundle. The inputs are the same. So here I have 3 and 3 in time period 8 and 1 and 1 time period 13. You'll notice that the index number for period 8 is 1.05, which is exactly 3 times the level in period 13 of 0.35. Again, it's working the way it should. 2 and 2 in year 14, we get an index number of 0.7, and that's twice 0.35. So it's saying we're using twice the input that we did in year 13. In year 19, 4 and 4, so we get 1.4. So it's saying we're using 4 times the inputs that we do in year 13 and twice what we do in year 14. So I'm confident that these index numbers are doing exactly what they're supposed to do, and the relationships we're getting are exactly right for this data set. So now that I've gone through all the index number creation and the DEA models, and I know it's a lot, I'm going to apply this. And so I'm going to apply it to the Northeast region. And I use this nice ecodata data set. It's produced by our ecosystem group, and they did a very nice job producing it. And it's in R, and so it fits in very well with everything else I'm doing. And so we had 3 outputs. I'm taking 3 outputs from this, and commercial fishing revenue represents the landings, recreational trips represents recreational opportunities, recreational demand, and then right whale populations is supposed to reflect marine mammals, protected resources outputs. The problem is that there are different time dimensions for these data sets within the database. So for example, we have revenue going from 1964 to 2019, and then we have recreational trips from 1982 to 2019. Now, if we just focus on those, it would be okay, particularly since these are divided into smaller ecoregions within the Northeast region. So there's like, I would get 4 data points per year from the revenue, and 4 from the recreational trips. And so I'd have a much bigger data set, and that's really important when you do these DEA models. But the problem came down to right whale abundance, because right whale abundance, we have 1 measure for the region per year. I took the median value from this data set. And so you can't really allocate it to different ecoregions because it's a level for the whole region. So for the outputs, we're really restricted to 1990 to 2019. For environmental inputs, I use levels of chlorophyll A. Some of the ecosystem modelers that have said that this is important, and so I use that. We have a Northeast Fisheries Science Center aggregate biomass measure from our survey, and then we also have measures of zooplankton. And so if you look at these environmental inputs, the chlorophyll A I had from 1998 to 2019. The aggregate biomass I had from 1963 to 2019, and then the zooplankton 77 to 2019. So we really got sort of limited in the length of our time series to 1998 to 2019, because that was the least common denominator, if you will, you know, to be able to include all these as outputs and then all these as inputs. So we took that data and we normalized it using the mean values, and that's just because there's such huge differences in the units. So commercial fishing revenue might be in hundreds of millions of dollars, and then wreck trips and well, right whale population levels are going to be like in hundreds, like 300. And so the environmental inputs also had that problem with just different, widely different units. So using the mean values made sense, or normalizing everything by the mean values made sense, I should say. So the we also bootstrapped our results, and I'm going to present to you the median values that come out of that exercise. So why bootstrap? So I was really interested in seeing if there was a difference in the outcomes before and after the last reauthorization of the Sustainable Fisheries Act. That took place in 2007. It was fully implemented in 2010, and really it made sense in that it was sort of a natural point to break off the analysis. So the other thing is that DEA scores are known to be biased, and we have a short time series. But you know, DEA scores, in most of the literature, you can bias correct them, and once you bias correct them, you can do statistical tests based on your bias correction, and the bias correction comes from that bootstrap. The problem with what we were trying to do is that most, in the literature anyway, the bootstraps that are done for DEA models are usually what they call subsample bootstraps, and we only had 22 years worth of data, so we couldn't do that. So we bootstrapped the whole data set, you know, randomly picking years, 22 years at each iteration. And so we had 2,000 replications. And so what I'm going to present is the median values and from that. And then we tested for the differences between those two time periods, both visually and with a Kruskal-Wallis test, which is a more formal statistical test. So here are my initial results. So they're really kind of interesting. So I'll start with the quantity index, the output quantity index. And you can see how it basically rose from 1998 to about 2011, and then it really dropped off. But still, if you look at the end of the series in 2019, we're probably doing about 15% better in terms of outputs than we did in 1998. So there's a definite improvement there. This is the environmental input quantity index, and it sort of divides into two parts. But after 2007, there was this increase, right? I mean, so when you get out to the end of the series, we're almost 40% better in terms of the state of the environment in 2019 than we were in 1998. So that's real encouraging. When you combine the two into that final index, though, you see this drop off beginning in 2006, and really it drops off until 2019. We're about 15% below where we were in 1998, and it's simply because this Q sub I, the output quantities dropped off. You know, basically the message I think to take away from this is that, you know, for this level of environmental input or environmental quality, we should be producing more or we should be getting more out of the ecosystem than what we are. And there's a lot of reasons perhaps why we aren't, but it would be better if we're up at a higher level. This index would be up if the output quantity index was up. So I kind of want to explore what was going on, what was happening to cause this, particularly the drop off in the output quantities. So I graphed them out, and so it's a really interesting trend. I mean, the commercial revenue, went down in 2006, but really it's sort of upwardly trended since then. So in 2019, we're above, probably 10% above where we were in 1998. And then if you look at right whales, I mean, you had this really nice upward trend till 2011, and then it dropped off. And it really, you think about right whales is so endangered, you really want to see this line keep going up and up and up, but it didn't. It dropped off. We're still above where we were in 1998, but this is a really troubling downward trend. And people who work in protected resources know this and are trying to do things so this doesn't happen. The wreck trips was really puzzling, and people haven't really fully explained this, and we're not sure why this is going on. It could be a matter of demographics. Like it could be that the population is aging, less people are fishing, less kids are going into fishing. It just needs more exploratory analysis. I also did the same thing with the environmental input quantities because I just kind of wanted to see what their trend there was like. And it's kind of interesting because this chlorophyll A is really flat. I mean, it's above where it was in 1998. But this zooplankton really, it was interesting, it went down, and then it just, this upward trajectory is really amazing. And really, you're getting like almost four times the amount of zooplankton in 2019 as you got in 1998. And then the biomass also has really been an upward trend. You're about 50% more in that survey biomass than you were in 1998. So those are both really positive trends. And so you can see why that environmental input quantity index was up and has sort of remained up. Finally, I plotted the quantity index, the output quantity index against this environmental inputs, and you see this nice upward linear trend. So it's basically saying that they are correlated. This is the Spearman correlation coefficient, 0.65, and then it's really significant. And so what you expect, what you could take from this is that, yeah, it looks like that these are positively correlated, and that if you have more environmental input, you should be getting more environmental output. The question I want to answer about the pre and post SFA, here's a simple histogram from our Bootstrap replications, and I just subtracted the post values, the pre-values from the post values. So if they were really, if nothing was going on, if there's no change, if they were pretty equivalent, you'd think that these outcomes would be stacked up around this zero line, right? But it's not. It's pushed all the way out here. It's this right skewed distribution, and with a really big chunk out here, which is about 0.22. So this might suggest to us that, yeah, things improved for outputs after Sustainable Fisheries Act came into being. And so for the environmental inputs, I did the same thing. And again, you see this here's the zero line, and then you can see this stack to the right. And so this again suggests that, yeah, environmental quality, I think it improved after 2010 in the post-SFA world. But then when you look at that final index, the environmental quantity index that we're looking at, you see here's the zero line, and you see it's sort of, it's more spread out. There's a lot of stacks here, a lot of observations here. This is about -0.02, but we do have some positive outcomes, and there's some that are further to the left. So this might suggest that really that there wasn't, that final index did not improve after the SFA was implemented. So I did a Kruskal-Wallis test. It's a more formal test of the differences, and the Kruskal-Wallis test is a non-parametric test, and it looks at tests whether the medians of two or more groups are different if they come from different distributions. I could have used this Mann-Whitney-U test, and when I tried to do it, there was a lot of ties, so R kept giving me warnings. But the Kruskal-Wallis test is fine. It gives you the same results. So the null hypothesis was both that both pre and post SFA have the same median values, and then the alternate was that they have different ones. And then the Kruskal-Wallis test uses a chi-squared value for the test. So the test for the output index was 8.04, and with 1 degree of freedom, which is what we have in this, you reject the H naught at the 0.1 significance level. So we're rejecting this null hypothesis of equal distributions. And then for the inputs, the environmental inputs, we has a value of 12.21, and we can also reject that null hypothesis. But for the EQI, the final index, its value is 0.278, and you can't reject this at any reasonable significance level. So, as we said, both the outputs and the environmental conditions seem to improve post SFA, but the final system measure did not. So just to summarize our findings, as I said, both outputs and environmental conditions really did improve during the 22 years, but after 2006, that combined index declined, and the final values were lower than 1998. Again, our pre and post SFA showed that the outputs in the environment both did improve after the SFA was implemented. The decline in that final index number during the last several years was really due to improved environmental quality, but declining environmental outputs. That's what caused the overall decline. But it's really important in this that really to understand more of the dynamics about the flow of benefits derived from the ecosystem. And then if we want to give this kind of advice to managers, we really have to focus on what's under the control and what isn't. So for example, the drop-off in wreck fishing may be totally due to an external influence like demographic change or a recession or something else that's causing that to drop, not what managers are doing. So we just have to be really careful about how we communicate this information to managers, that telling them what is in their control and what isn't. In terms of potential future work, cross-regional study, we've been working on that with the human dimensions working group, perhaps, but the ecoregions are different in size. So in the Northeast, you have this huge human population, which was going to dwarf that which would be found in Hawaii and that in Alaska. And so the resources are different, the population sizes are different. But I think if we focus on growth rates, so we look at our index in terms of change in output growth divided by change in input growth, I think that's the way to get around that problem. Our indicators, there's a problem when you don't have enough observations for your outputs and inputs in the DEA model, but this free disposal hull method you could use to construct indicators, and that's based on a enumeration technique with the data, so you don't have this problem that's due to not enough observations. Just have to do some more research about this because you give up some other assumptions when you do this kind of model. I think really I personally want to focus on constructing some of these indices for just the fishing sector to help the councils in their decision making, because I think that we have enough data in the Northeast that we can do that. And finally, this particular index, there's a more general form of a distance function you can use, a directional distance function, and I think we can use them to construct some risk metrics that I think would be kind of interesting to do. So just in conclusion, say index numbers, I think really can provide some meaningful comparisons of performance through time. I think our advantage is the weights for the outputs and environmental factors are endogenously calculated, so you don't have to try to come up with weights beforehand. Some caveats: you really need to think about the linkages between the outputs and the environmental factors, if they're related or not. And then you have to think about if this is going to be for managers, what outputs and inputs are under their control. And ultimately, this is really a benchmarking exercise. So you really need to give some thought about the appropriate benchmark, whether it's a spatial or a spatial dimension or time period or some other combination of that. So if you knew that a particular year or a particular ecosystem did really well, you could use that for your benchmark. So I'd just like to thank everybody for your attention, and I'd be happy to answer any questions that you might have at this time. Thank you.
Thanks. Just to remind everyone, you can put your questions in the question panel and go to webinar. And we do have some questions coming in here. All right, have you looked at how indices have tracked or not with large-scale forcing such as ENSO events or warming trends in the Northeast?
For the Northeast specifically, no, I don't think we have. I know in the Human Dimensions Working Group, we're working on that with the cross-regional model, and I don't think we've done this. We certainly can do it. Garrett's worked on those models for the larger group, and we haven't done it in this case yet, but it's a good idea. We could.
Okay, and I'm just going to wait a few minutes to see if anybody has any additional questions while people are typing. Okay, our next question. Efficiency may not be the most important metric when dealing with fishing communities or cultural values. Any way that this method can incorporate other values?
Yeah, I mean, it's not designed around efficiency per se, I don't think. You can use the distance functions in the same way for community values. So, that there are examples where other human dimension inputs or outputs have been used. So the DEA model, you're right in a sense. I mean, the DEA model basically will give you the best outcome given your environmental input. So if part of those outcomes are community-based indicators, and I don't know what you might want to use, like employment, okay, or revenue at the community level, the DEA model is going to give you the best outcome given the environmental factors. So that's how they're being made part of the system, and then those DEA outcomes are basically used to form the index numbers. So yeah, you can put community-based measures in there. In this case, we just didn't. I don't think we had the ones we'd like to use if we were going to do that.
Okay, thanks. I don't have any questions here yet, but I'm going to wait another minute. All right, is there more guidance for variable selection? Is it naive to think that including more variables as inputs and outputs would have more accuracy as a time tracking index of overall system performance or more explanatory power for shifts through time? And I'm going to copy this question and put it in the chat for you, John, because it is a multi-part question.
Okay. How do I see the chat?
Sure. It should be at the bottom of the panel, and I can read it for you again if you'd like.
Oh, okay. I see it now. Yeah, I see it. Sorry. So, for this particular, this was a proof of concept. So I was just trying to find as much data as I could, I think, and trying to make have some relationship between the outputs and the inputs. So the problem with with using DEA for this is that it's very data hungry in a sense. So, as you increase the number of outputs, let's say, you have to increase the number of observations. So it made it hard. It was sort of like we really had to balance the trade-off between, what we could include and the length of our time series, and that's what made it hard. I'm not sure if if you get more explanatory power, I think that you would get you probably get a better index in some sense because you're incorporating more values, right? So you can say that index included more things. I'm not sure if it would explain it any better or not. It's sort of something that I think needs more work to really see the answer to that.
All right, so this looks like it's going to be our last question here. To the previous questions on temperature, are there fundamental changes that change the relationship between the inputs and outputs such that it changes the production possibilities frontier, or is the DEA model robust to those changes?
So there's lots of ways to do this DEA model, and yeah, there's ways you can do it to have an environmental factor like temperature change that would probably affect the index. So for instance, when you talk about like temperature change, that's a change in the environment. It's sort of similar to like a technical change in economics, right? It's something that has a possibility to shift that production frontier up and down. Now, in the particular way I did it here, I didn't do that. But there's methods out there certainly that you could use that could try to get at that using sea surface temperature, sort of a shifter of that frontier, and you could write your DEA model so you could get that that shifter as a technical change component, I guess you'd call it. This particular example that I used and put together, it was we're trying to get an index that we thought made sense over time, and we're sort of limited by the data that we had, and it just turned out we just didn't have the length of time series that I would have liked, and if we had a longer time series, we might have been able to incorporate temperature and done the DEA model a little differently. So I hope that answers the question, and if people want to email me more about it, we could go back and forth.
Great, thanks, John. So that is the last question that I have here. Let me double check. Oh, we do have one more. Do you think the differences in data quality / methods over time are impacting results, or the comparison of the indices over time?
Yeah, I thought the data quality I thought was pretty good. I thought that this eco data base that I had I thought was quite good. I wish that the time series, I guess to answer that question, I wish that the time series for some of them, some of what we used were longer. Like that's a real problem. Like when you have data that, you have this long time series for commercial landings going back to 1964, but you don't have any other outputs that go back that far. And then, this problem with protected resources, I don't mean to say problem, but it's just so the way the data are, you have one value per year for the region, and then how do you deal with that? Because the commercial landings data, I could have expanded that data set greatly and looked within the Northeast region and done it by ecoregion. But the fact that I couldn't do that really with the marine mammals made it more difficult, right? I couldn't expand that data set more because I was limited to one observation for the right whale per year. So, I wish I had that same right whale data going back to 1964 too. It just ended up being sort of problematic for the way we want to construct these indices.
All right, and we do have time for more questions, and there are more here. So if you have another question, just type that in the questions panel. We have a couple of minutes. Is there an option to use satellite remote sensing data for proxy inputs to time periods where other observations/data does not exist?
Sure. I guess I'll plead ignorance on what's out there for the satellite data. I didn't explore satellite data. I guess sometimes in our fisheries world we're too stovepiped in a sense. Yeah, you could use if we had good satellite data. Yeah, we could use that. I don't see any reason why we couldn't.
Okay, so it looks like that was the last question. So we are going to wrap it up. Thank you, John, for joining us today. Thanks, Peg. Let me just say you will be able to find this presentation on YouTube later this afternoon or evening. When the presentation ends, you'll see a survey. If you could take time to fill that out. We do use those surveys to improve marketing the library seminar service and to improve the seminar topics. Thank you again for joining us. Have a great rest of your day, everyone.
Thank you, John. I appreciate that. And I also stay tuned for May 11th. Our next speaker is Tori Kettner from the Northeast Regional Science Center, and she'll be focused in on the Northeast Regional Habitat Assessment Project. And I think there'll be a lot of folks to be interested in that. So again, thanks to John and Garrett. Appreciate all your efforts in the presentation. Excellent job.
Thank you, everybody, for attending.
Thank you.